Good morning or good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is Sam Moulton from the Business Review, and I will be your host. It's our pleasure to have Evoqua Water Technologies with us today, who will be discussing advances in clarification technology in water and wastewater treatment. Today's guest speakers are Robert Backman, Senior Technical Manager, and Kevin Warhite, Industrial Inorganic Wastewater Product Manager. But now, without further ado, please let me welcome Robert.
Thank you, Sam, and good afternoon and good morning to everyone, and thank you for joining our webinar today as we talk about advances in clarification technology. We're all familiar with using sedimentation or clarification for solids removal for either treating processed water or wastewater or other types of water. We want to remove the solids from the water to generate a desired effluent. And the solids we typically are trying to remove are either biological or physical chemical generated solids, and they have a specific gravity of about 1.02 to 1.03, very light and fluffy, very close to specific gravity of water. And under conventional clarification processes, you can generally get a good quality effluent, but there are a variety of things that can cause a process upsets. They can be related to hydraulic issues, mechanical issues, or in a biological process, they could be biologically upset process issues, which ultimately result in you not receiving your desired effluent quality. And to overcome those challenges, you typically either have to add larger surface area clarifiers or a downstream tertiary filtration step. But what about if we could just add weight to those solids so they settle readily in a clarifier? And that's what we'd like to talk to you about today, the ability to ballast clarification steps to get better settling effluent and achieve a desired effluent quality. Now, the two processes we want to talk to you about today, the first is called BIOMAG, and that is ballasting any activated sludge process to settle out readily in a conventional clarifier of biological solids to achieve a higher level of effluent quality than you normally would through conventional processes. And the second one is called COMAG, which is really just an enhanced high-rate coagulation flocculation treatment process using a very high-rate clarifier or small footprint clarifier, or the ability to get more capacity out of existing clarification step. Now, ballasting technology is not new. It's been around for many years. Initially, people had used bentonite and then microsand or sand particulate, and this is kind of the third generation of ballasted technology, using magnetite as a ballast. And I'll explain the magnetite ballast and the characteristics of it in a minute. The technology originally developed in Cambridge, Mass. Back in the early 80s and commercialized in the 90s with the COMAG process, and shortly thereafter came up with the activated sludge process called BIOMAG to ballast any activated sludge process. The best way to show this technology is to show you a quick video here, and this is actually a COMAG installation used in this instance here for tertiary treatment for phosphorus removal. And what I want you to vision here is to see the solid settling right off the center well, and normally you couldn't do this in a clarifier. You couldn't put an underwater camera in and actually show the solid settling. So for the next 30 or 40 seconds or so, you'll see this video, and I'll let it run by itself and demonstrate the ballasted technology. Now, as this video is running, this is a high-rate clarification step, treating about 5 mgd through an 18-foot clarifier. And you can see the ballasted solids settling right off the center well of that clarifier. Now, in both of our ballasted technologies, we're just adding enough weight to the solids to increase their specific gravity to about 1.2 to 1.3. Now, the ballast we use is called magnetite, and it's mined all over the world. It's used in a variety of different processes. One of the largest users of it is the coal industry. They call it coal float, and they use it for very similar reasons that we do, because it's fully oxidized iron, Fe3O4. It's non-abrasive. The only specification we have where you can buy it as a bulk or you can buy it from Evoqua itself is a size specification. The particle size are all smaller than 30 micron, very similar to talcum powder or toner cartridge. Now, the reason we use magnetite is, first, it's inert, fully oxidized iron, but has a specific gravity of 5.2, about 2.5 times that of sand or grit. Now, because it's charged neutral and chemically inert, it's actually hydrophobic. And what that means is it doesn't fit well in the water polar matrix, and it rarely gets attracted to solids that are in there and gets embedded in those solids and increases that specific gravity to about 1.2, 1.3. It's pretty inexpensive, about 30 to maybe 50 cents a pound delivered anywhere around the world. As I said, it's mined all over the world. Its source is readily available. And obviously you're adding weight to solids, and when you dispose, because you're pulling solids out of your treated water, you need to dispose of those solids. You don't want to increase the weight of those solids and increase the cost of disposal costs. So we go through a process recovering the magnetite and putting it back in the process again. And the way we recover it is we take advantage of it being fully oxidized iron and use a magnetic field, and Kevin will explain the process of recovery later on in this webinar, and recapture the magnetite and put it back in the process again. So you're essentially just disposing of the generated biological solids or chemical solids. Now, the process of getting the magnetite into either BIOMAG or COMAG is pretty similar and very similar in both processes. You generate solids, whether you're going through a flocculation step or a biological process. We have a mixed tank where we add the magnetite in and mix it up for a couple of minutes, and it gets readily impregnated into the floc particles or penetrate into the floc particles. Increase their weight so they readily settle. Go on to a high-rate clarification step to get the solids to settle out, which allows you to typically run at much higher surface overflow rates or solids loading rates on clarifiers than you normally conventionally would, increase its capacity of treatment of existing clarifiers, or give you enhanced effluent quality. And typically, because it's reduced footprint versus other alternative solutions to overcome your challenges of treatment or process water treatment, it's typically a lower capital and O&M operating costs versus other conventional methodologies, which may be large clarification or filtration steps. Now, this process, as I mentioned earlier, is very similar with COMAG or BIOMAG. If you look at the two microscopic pictures on the right there, you'll see floc particles, and in the lower right is a floc particle with the magnetite impregnated in it, and on top after recovery. So as you can see, it's still very similar floc characteristics as you normally would have with a chemical floc or biological floc. We're just peppering it with magnetite to increase its specific gravity. Now, as I mentioned earlier, this technology is not new, and this is just an example in North America. We've got a variety of installations of both BIOMAG, both in industrial and in municipal applications all across North America, as well as installations in other parts of the world. For example, we have BIOMAG and COMAG installations over in the UK, and we're currently working on installations in Singapore as well as in Australia. So the technology has gained a great foothold in applying with challenges that can be needed to be treated all across the United States as well as in other parts of the world. Now, in summary again here, just to explain the two technologies before we do a deeper dive into them, BIOMAG is ballasting any activated sludge process, and that can be a variety of technologies, whether it's a sequential batch reactor, SBR, or a conventional or high-rate system, and enhance its capabilities and give you more capacity if need be or more reliability out of that process without adding more tankage, more infrastructure tankage, using the existing tankage that may be available in a brownfield application or in a greenfield application, reducing the tankage requirements because we can run at a much higher mixed liquor than you normally would. Now, COMAG is a superior solid separation high rate using conventional clarification processes for treating both produce water or drinking water or wastewater applications, removing particulate or precipitated solids in a small footprint clarifier. Now, unique to COMAG versus other technologies, ballasted technologies, is we can use any type of clarification and still achieve a high level of effluent quality. So if there's existing clarification or sedimentation processes, we can reuse those infrastructure and gain you more capacity or better performance out of those processes. Now, what I'd like to do here is turn it over to Kevin Warheit to spend a few minutes talking through the COMAG process, and I'll be back with you later in this webinar to explain BIOMAG and then close out with answering your questions. So Kevin, I'm going to turn it over to you now.
Okay, thank you, Bob. Good morning or good afternoon to everyone. As Bob mentioned, I'm going to be talking about the COMAG process, mainly towards the industrial applications. If we look at a simple clarification process, a coagulant such as iron, aluminum, or calcium, and a polymer is added to a wastewater treatment stream, and the flocculated particles are sent to a clarifier. Since the flocculated particles are fairly light, a large circular gravity clarifier is used. A lot of the retention time in the clarifier is required to allow for the particles to settle to the bottom of the clarifier by gravity. To enhance the settling rate of the flocculated solids, a ballast media is added to the precipitated particles to allow prior to the addition of the polymer. In this case, magnetite is used as a ballast media. The magnetite is added after the coagulant but before the polymer in the ballast media reaction tank. To further enhance the nucleation process, a portion of the sludge from the clarifier is recirculated back to the ballast tank. This will minimize chemical addition and promote solids contact and further aid in nucleation process. Since the Fe2O4 is magnetic, the magnetite is mechanically split from the sludge and recovered on the magnetic drum, where the recovered magnetite is returned back to the ballast tank. Up to 99.9% of the magnetite can be returned back to the system. The magnetite-free sludge is sent to a sludge dewatering process. Since the magnetite is 5 times the weight of the flocculated particles, it will rapidly settle in a matter of a few seconds, resulting in a smaller clarifier. Also, throughput capacities can be increased up to 10 times without compromising the effluent quality. A closer look at the multi-stage reaction tanks reveal a 3 to 10 minutes retention time in the coagulation tank. That's the first tank on the left side of the reaction system shown in the center of the slide. And there's a 3-minute each retention time in the ballast and polymer addition tanks. The flow is directed over a baffle from the coagulation tank to the ballast tank, and underflows from the ballast tank to the polymer tank to prevent short circuiting. Either a small circular clarifier with a sludge rake or rectangular clarifiers with plate packs or tube settling media can be used as a solids separating device. Between 15 to 25% of the sludge from the bottom of the clarifier is recirculated back to the ballast tank. An additional 2 to 5% of the sludge is fed to a shear mill, where the magnetite is separated from the sludge and then recovered on a rotating drum. As mentioned before, the waste sludge minus the magnetite is sent to a sludge dewatering device. We're going to look at another video here. This video will show how magnetite added to flocculated particles can greatly enhance the settling rate. Now, depending upon the speed of your network, there may be a slight delay here in the video. So Bob will let me know when it pops up because I am showing a delay on my computer.
Kevin, it's running now, and I would let it go the full 50 seconds. That way, hopefully everyone sees a good 30 seconds of the enhanced settlement characteristics.
Okay, the beaker on the left represents a conventional precipitation process. The beaker on the right is using the same wastewater, but the flocculated particles are impregnated with magnetite. As we can see, after about 30 seconds, a vast majority of the particles have settled in the beaker on the right. Even after a minute, very little solids have settled in the beaker on the left, whereas all the solids have settled in the sample containing the magnetite.
Kevin, I believe you can advance the presentation now.
Thank you, Bob. The COMAG process is capable of removing a wide variety of species. Typically, if it's insoluble or can be precipitated, COMAG can remove it. The heart of the system is a stainless steel magnetic drum separator. As mentioned before, waste sludge passes through a high shear mixer, which breaks apart the flock, separating the particles from the magnetite. The mixture passes over a magnetic separator drum, which captures the magnetite and returns it to the ballast tank. Up to 99% of the magnetite in the waste sludge can be returned back to the system. A closer look at the recovery drum, we see that on the inside of the drum is a fixed array of rare earth magnets. As the magnetite is separated from the sludge by the inline shear mixer, the sludge is directed over the surface of the drum, where the magnetite adheres to the surface of the drum by magnetic attraction, and the free sludge is collected in a waste sludge compartment. As the drum rotates, which is about 8 RPMs, the magnetite that is fixed to the face of the drum is scraped off using a rubber doctor blade and returned by gravity back to the ballast tank. Typical applications, the recovery drum is typically installed above the ballast tank. As a result of adding magnetite to the process, solid settling rates can be 20 to 40 times faster than conventional settling technologies, resulting in lower hydraulic retention times in the clarifier, which means the clarifiers become smaller, saving valuable real estate. Since a high inventory of suspended solids is maintained in the ballast tank, and typically this can be anywhere from 5 to 12 grams per liter magnetite, low concentrations of suspended solids, or TSS, in the feed water does not become a problem. The recycled sludge also seeds reaction chemistry and produces high-quality effluent. Typically, we can see less than 0.05 milligrams per liter of phosphorus without any further polishing steps of the effluent. If the contaminants in the water or wastewater are insoluble and can be precipitated, such as heavy metals, then COMAG can usually remove them. In some instances, for oils and greases, pretreatment such as oil water separations or dissolved air flotation units may be necessary prior to solids removal through the COMAG process. Soluble constituents such as sodium, chlorides, and volatile organics will not be removed by the COMAG system. Looking at a size comparison of a typical 700-gallon-a-minute conventional field-erect circular clarifier versus a shop-fabricated rectangular tube media clarifier, it can be seen from the slide that the field-erect clarifier takes up to 14 times more space than the shop-fabricated clarifier using the COMAG process. As we all know, footprint is a prime concern when designing wastewater treatment systems. COMAG is provided in a number of configurations. 4 standard pre-engineered shop-fabricated skid systems are available for flows up to 5,000 gallons per minute. For larger flows, custom engineered systems are available using field erect steel or concrete reaction tanks and clarifiers. For existing systems where flow rates or high solid loadings have become an issue, retrofits could be a good alternative instead of installing a new system. Hydraulic profiling and torque conversions considerations on the drive motors and reg mechanisms must be investigated to ensure proper operation of the system. For temporary applications, trailer-mounted mobile units are available for flow rates up to 1,600 gallons per minute. With flows up to 5,000 gallons per minute, single or multiple shop-fabricated skids can be used. As shown in this slide, the shop-fabricated skids consist of three-stage pretreatment skid, which contains the coagulant ballast polymer reaction tanks, and also included are the inline shear mixer, the recovery drum, and the chemical delivery systems for the coagulant, acid, caustic, and polymer, as well as the electrical control panel. Also included is a rectangular clarifier, either using plate packs or tube settling media, a sludge recirculation pump to direct the sludge from the bottom of the clarifier to the ballast tank and also to the shear mixer and recovery drum. Since the standard units are shop fabricated, installation, startup times are greatly reduced compared to custom designed field erect systems. COMAG can be applied in a wide range of applications and markets. Surface water treatment for the removal of TSS, which is total suspended solids, phosphorus, color, and algae is a prime pretreatment example prior to boiler water feed, cooling tower makeup, DMIN, and RO technologies. It can be utilized in various wastewater applications as well to remove heavy metals and phosphorus. It is applicable in a wide range of markets such as power, mining, solar, and microelectronics. In the next 4 slides, we will be discussing 4 case studies. The first case study we will look at is a mining application in the Midwest part of the United States. The objective was to treat processed water to enhance water recycle and reuse by removing suspended solids and colloidal suspensions. At the start of the project, a successful pilot was done to demonstrate proof of process. As a result, inline shear mixers, magnetic recovery drums, and a 70-foot diameter circular clarifier was installed. Not only were they able to meet their objectives, but they were also able to increase the yield of their product from their operations. The client partnered with a well-known engineering firm from the Northeast to help them execute the project. The second case study is a COMAG application that was a retrofit at a large semiconductor manufacturer. Due to the expansion of manufacturing, the wastewater treatment system had to be increased by 2.5 times, basically from 60 to 150 gallons a minute. The system was originally designed to treat hydrofluoric acid using lime. Since space was at a premium, the expansion had to take place in the original space that the wastewater treatment system already occupied. The system was retrofitted with duplex inline shear mixers and duplex magnetic recovery drums. The existing lamella clarifier was modified, and they used the existing reaction tank system. The turbidity from the clarifier effluent resulted in an NTU of less than 0.5, which was much better than the effluent from the original wastewater treatment system. The next case study we're looking at is an application to remove algae from a lagoon. After the addition of a coagulant, the TSS was about 130 parts per million. Once it was processed through the COMAG system, the TSS was reduced to less than 5 parts per million, and the phosphorus was also removed down to less than 1 part per million. The final case study we'll look at is a surface water application where the goal was to remove total suspended solids, turbidity, arsenic, iron, manganese, and true color. The surface water application had a wide swing in turbidity. Recycling the sludge back to the ballast tank was a key in reducing the turbidity, especially when the turbidity were at very low levels. Now, at this point in the presentation, I'm going to turn the presentation back over to Mr. Bob Backman, who will discuss the BIOMAG technology with you.
Thanks, Kevin. Just take a quick pause here, and I saw one question came up, and maybe you can comment on. The question was pertaining to using COMAG and the ability to use existing clarification processes. So could you comment on that and the ability to do that?
Yes, we have retrofitted a number of installations with the COMAG process. Some things need to be considered. If you're increasing the flow rate, you have to ensure that the upfront pretreatment system is large enough to handle the appropriate retention times. As mentioned before, because we were adding magnetite, which makes the sludge heavier, you have to make sure the drives are beefy enough to handle the extra torque on them, and also that the structure of the rake is stout enough to handle the extra torque. And then also you want to check the nozzles on the clarifiers to make sure it can handle the higher flow rates or the higher solids loadings.
Thanks, Kevin. And just to comment on that statement, we have done many retrofits with COMAG using existing clarifiers, whether it's a conventional rake-style clarifier or a rectangular-style clarifier. And actually, in many of those instances, not replaced the rake mechanisms. As long as they're mechanically sound, we've been able to reuse those existing mechanical rake clarifiers. And not change those out. Now, in some instances, because of their age and mechanical integrity, they were decided to be replaced. But quite often, we've been able to use existing clarification capabilities, at least the tankage. So what I'd like to do now is spend a few minutes talking about BIOMAG. And BIOMAG has really overcome one of the major bottleneck in any activated sludge process, and that is consistent settling of biological solids, because there's many things that can cause biological solids not to want to readily settle. It can be biologically related to filament or sludge bulking issues. It can be Nocardia outbreaks because you're trying to do enhanced nutrient removal and require long sludge ages, and you have issues where you get Nocardia and foaming issues. And then typically the clarifier is the Achilles heel of the bottleneck of the system. And BIOMAG overcomes that bottleneck. And to demonstrate this is actually, I'm going to show a quick video here of biological sludge settling, and I like to call this my 30-minute settling test, done in about a minute or so. And this is a process that we're actually running right now, an activated sludge process. And I'll set up the video. It's about 6,000 milligrams per liter of mixed liquor solids, and we run BIOMAG at a 1-to-1 ratio. So biologically determines the amount of mixed liquor you need to have in your process. All we do is maintain a ballast in there at a 1-to-1 ratio. So if it's 3,000 milligrams per liter of mixed liquor, we'll maintain 3,000 milligrams per liter of magnetite in the process, so a total TSS of 6,000. Now, because the magnetite gets embedded into the biofloc itself really flows very similar to 3,000 or 6,000 milligrams per liter of solids. It just settles a lot faster than it would conventionally. So from a pumpage standpoint or movement around, it's very similar to the mixed liquor concentration because the floc particles are still roughly the same size. And to show you that enhanced settling, let me quickly jump to this video here and let it Now, the application of BIOMAG is pretty broad to any activated sludge process. Biologically determines what type of biological process you're going to run. If you're trying to remove just BOD, it could be a conventional high-rate system, or COD that's biologically removable. If you have to do an E&R process and remove phosphorus or nitrogen to do denitrification and nitrification, you may run an oxidation ditch or a multi-stage type process. We've done quite a few SBR upgrades to enhance the settling cycle, take time from settling and put it back into react zone, and ultimately drive so you get enhanced effluent quality coming off if that's your need from a discharge standpoint on treating your biological wastewater. Now, one of the advantages, because we are able to run at a much higher sludge age and get an enhanced process here, is quite often we can drive what's called simultaneous night-denite. And I won't spend time today to get into that, but it allows you to get more enhancement out of your process, more nitrogen removal, and more stable effluent quality. Now, to understand the process itself of BIOMAG, we're all very familiar with activated sludge processes. You'll have a bioreactor, and that may be broken into zones, or maybe aerobic or anoxic zones. That mixed liquor coming out of that bioreactor will flow to a conventional clarifier. Now, as with COMAG and BIOMAG, we can use a variety of clarification processes. They can be conventional, reg style, rectangular, or they could be a Tobro type, suction type of clarifier. Now, because you're running a biological process, the biological process will dictate the biokinetics, the amount of solids you need to maintain, mixed liquor solids you need to maintain in the process, and your desired sludge age. So you're going to return solids through the process. Now, if you have an increase of your influent flow or contaminant loading on your clarifier, you may have to run at a higher mixed liquor or a change in temperature. And that may result in where you're getting close to a solids loading capacity limitation on your clarifier. And when you do that, you're going to see where you may start seeing solids start floating up out of your clarifier. For example, if I had to increase the mixed liquor to 4,000 milligrams per liter from 3,000, I'm going to start seeing some solids start floating up in that clarifier. Now, when that happens, if I had to go even further, and let's say I was needed to run at a higher mixed liquor sludge age because I wanted to nitrify and denitrify, I'm going to overload my clarifier, and ultimately I'm going to see solids leaving my clarifier. And when this happens, I now have a bottleneck being my clarifier. Now, I'm either going to have to overcome that, add more clarification surface area, or more clarifiers, or more bioreactor volume. But with BIOMAG, by adding a simple process of being the ability to add magnetite into the process, and we have a feed system called a silo, and that can come in a variety of sizes depending upon the size of your activated sludge process. We ballast those solids so they settle more readily in the clarifier. You can still use your conventional RAS pumps to return mixed liquor to the front of the process. You still run the processes you normally would biologically. Now, obviously, from a biokinetic standpoint, you need to look at and make sure you get enough aeration capacity in your system to meet the oxygen demand. And quite often, it becomes oxygen limited before it becomes mixing limited. So you have to add more aeration capacity to meet that oxygen demand. So you're not adding any additional supplemental mixing. And you run your process as you normally would, but allows you to eliminate those carryover solids and achieve a high level of stable effluent quality. Now, because you're generating biological solids, because you're removing BOD or COD or nitrogen, you got to waste solids. And when you go to waste solids, we go through a very similar recovery step. We go through a shearing step, as Kevin mentioned earlier, separate the magnetite from the biofloc. Very similar recovery drum as you saw earlier. They come in a variety of sizes depending upon the wasting rate. So the size drum can be anywhere from 18 inches in length up to 6 feet in length. And recover the magnetite and put it back in the process. Now, with the BIOMAG process, we're typically going to see somewhere between 97 to 98% recovery, a little less than you would with COMAG, but still very economical from a process standpoint because magnetite's pretty inexpensive, as I mentioned earlier, somewhere between 30 to 50 cents a pound delivered to site. And then your WAS will go off to WAS handling. Now, that could be either dewatering or it can be anaerobic digestion. Magnetite is not regulated in North America, so it can be land applied or land filled. Magnetite is an earthen material. It's actually already applied to a variety of land applications now. For example, industrial fertilizers, dry fertilizers, use magnetite as a ballast so the fertilizer doesn't blow away. And that's the BIOMAG process itself. Now, really what we're doing here is overcoming the clarifier bottleneck. And we're also familiar with clarifiers. You have an influent into that clarifier. And for example, here I'm showing an upflow clarifier. And you'll have WAS coming off the bottom, or RAS pulling off the bottom of the clarifier after the solids settle, and an effluent coming off the launderer and weirs on the top. And really what we're doing with BIOMAG is driving those solids so they settle readily in that clarifier and increasing the solids loading on a conventional secondary clarifier from 5 to 20 pounds per day per square foot to as high as 120 pounds per day per square foot. And if you look and analyze a clarifier, one of the things you normally will look at is what's called solids flux or state point analysis. And if you look at a state point analysis curve, it will generate what's called a solids flux curve, and you need to have your loading in that clarifier below that curved line. So if you were to plot your effluent flow and your underflow out of that clarifier, where those lines intersect, provided it's below that solids flux curve, your clarifier is going to properly perform. Now, if I increase my flow hydraulically through the plant, I'm going to exceed above that curve, and I'm going to start washing solids out. What BIOMAG does, because you're able to get the solids to settle faster, is take that solids flux curve and increase it, spread it out, and increase it higher, so that I now fit within that solids state point analysis, and I'm able to get more stable settling in that clarifier and achieve my desired effluent. Ultimately get more capacity both hydraulically and solids through that clarifier. Another way to look at it is if you were to plot what's called a capacity curve, aeration tank capacity and a clarifier curve based on mixed liquor and hydraulic capacity. Where those two lines intersect is the capacity ultimately of my system. What we're doing is taking that clarifier curve and pushing it out and giving you more capacity out of existing infrastructure. Another way to look at it here to explain BIOMAG so you have a good solid understanding of it is the ability, we're not adding more tankage. If I double my throughput through the plant from a hydraulic throughput, which increases my solids loading or organic loading on the plant, and now you need to maintain my desired F to M ratio, I have to run at a higher mixed liquor. And with the feed recovery system, I'm not adding any more tankage to the process. I'm ballasting those solids so they settle readily in a clarifier. Increasing that loading on that clarifier to 100 to 120 pounds per day per square foot and still achieving less than 10 TSS and very low BOD and a high level of effluent quality off the back end. We've done quite a few BIOMAG retrofits to existing applications that have had needed increased capacity, both hydraulically as well as treatment performance. Go from conventional to E&R, enhanced nutrient removal, to carve up the tankage and put in anoxic zones so they can nitrify and denitrify. And ultimately, it gives you the ability to run your mixed liquor up as high as 8,000 milligrams per liter in the existing infrastructure tankage without adding more concrete and more footprint requirement to your process. Now, as far as the footprint of the capacity of the equipment, with BIOMAG. If you look at an example of a plant here, you can see the infrastructure of the tankage there on the lower right in the picture. To double that capacity, from a footprint standpoint, that little blue dot that you see there would be the BIOMAG equipment, and as you see on the right-hand side, it would be the recovery drum, what's called a ballast makeup tank, and that's where we remix the magnetite with RAS or a slipstream of RAS or slipstream out of your biological reactor, get the magnetite, both makeup and recovered magnetite, back into the biofloc and put it back in the process again. Essentially doubling the capacity of that plant without adding a large footprint requirements. You still have to look at, obviously, your handling of the front end of the plant as well as your solids handling capabilities, but I don't have to add all that additional tankage. Now, when you go through the process and increase mixed liquor, quite often people are concerned about, and may be familiar with MBR type processes. As you increase mixed liquor, your oxygen transfer efficiency will reduce. Now with BIOMAG, magnetite does not inhibit oxygen transfer, and that's what this curve is showing you here. It ultimately, the mixed liquor will, but magnetite itself will not. So if you have a conventional 4,000 milligram per liter mixed liquor process and you put in a BIOMAG process and increase the mixed liquor to 8,000, you're still going to have the same oxygen transfer efficiency with that aeration device as you would with conventional if you add BIOMAG to it. Now, if you look at the application of BIOMAG, it can be used to increase capacity, free up tankage so you can get nitrification, denitrification, the ability both biologically or chemically remove phosphorus, handle high peaking factors if you have hydraulic surges through your process, so you're not going to wash out solids in your process, and ultimately overcome the other issues typically with a conventional biological clarifier. Bulking issues, etc., filaments are very common. They still will readily settle in your process. And if you have to add capacity, able to do it in a very small footprint and overcome site constraints. As a couple of quick examples here, a footprint constraints. This was in a facility that's implementing BIOMAG at it. Now, this is a municipal application, but it could be an industrial application also. They have an increase in capacity. They also have a tighter effluent limit requirement. They are now going to have a nitrogen and phosphorus limit. And conventionally, they've had to add 4 more clarifiers and almost double their footprint of activated sludge reaction volume. With BIOMAG, they only had to add a very small, about 75% reduction in bioreactor volume, what they would have conventionally, so add just about 25% more bioreactor, and 2 additional clarifiers, substantially smaller footprint than what they would have had to do conventionally, and obviously reduce down their clarifier by 50%. And it was very economical and from a CapEx and OpEx standpoint versus going conventional. And so they've chose to go with the BIOMAG process and not needing downstream tertiary filtration requirement. Another example, case study is freeing up tankage, as I mentioned earlier. This was a facility that had package-style donut shape extended aeration process. We're going to get a nitrification and a phosphorus limit and needed to double its capacity. Using existing tankage, existing clarifiers, added new aeration to increase the aeration capacity, very tight footprint and very economical. Achieved this with using an existing footprint, and ultimately ended up achieving a higher level of effluent quality than what they really were trying to do at no additional cost, because we were able to drive what's called simultaneous night-denite. As you can see here, from a standpoint of total effluent, they're averaging about 5 milligrams per liter. Their target was 10, and pretty consistently around 5 average. And actually, they can get much lower than that if they really want to drive the S&D and get it down to a much lower effluent quality. Upper Gwinnett is another facility that saw a substantial increase in its hydraulic loading. We're going to have to double its clarifier capacity and put in sand filtration, but by using a very small footprint feed recovery system with BIOMAG, they didn't have to add additional tankage, and also ultimately meet their new permit limit for phosphorus without tertiary filtration, and achieve a high level of stable effluent quality. As you can see here, very low turbidity, using turbidity as an indicator, even during high peaking factors where they saw the flow up to 15 MGD, wet weather flow capacity. Showing the high peaking factors, this was actually a demonstration of that high peaking factor at this facility. And if you look at the picture on the left there, you'll see a very turbulent center well, putting it close to 7 MGD through an 85-foot clarifier. And you can see on the right there, the solid selling right off the center well. So we achieved less than TSS, very low BOD, and actually total nitrification, even during this high peaking condition. So able to do this without adding substantial infrastructure to the existing facility, and very economical. Now, one of the things with BIOMAG is adding stability, more robustness to your biological process, and overcoming those things that I like to call cumbersome or bottleneck to activated sludge process, filaments, etc. And the ability to do that not only in a conventional activated sludge, but very common with SBR processes or shallow clarifiers where solids don't want to readily settle. BIOMAG can overcome that and give you a consistent high level of effluent quality, whether it's a variation in the industrial load that you may not be able to control, so your loading to your system may vary up and down, or you may have septage or other things that come into your facility that can be very cumbersome to want to settle readily in a secondary clarifier. By ballasting, because of the inertness of magnetite and the hydrophobic characteristics of it, it gets readily penetrated into the biofloc and will settle. And show you just a clarifier here of non-ballasted and ballasted, a high-level effluent quality coming off of that clarifier. As an example of ALLENSTOWN, once again, just overcoming another characteristic of clarifiers, look at SVIs, very high SVIs at ALLENSTOWN and up to 300 to 500 at times, but once they implemented BIOMAG at it, very consistently below 100. Now, obviously, when you look at a biological process, BIOMAG is just one component of it. Because we want to make sure that the overall installation will be effective in operation of it, we typically will do what's called a flow sheet design. Look at the RAS pumping, the piping sizes, your clarification, your aeration capacity, et cetera, and make sure it's appropriate for the technology of BIOMAG, and make sure that you're going to get a very efficient, very reliable process. So we'll do that engagement either ourselves or with an engineering firm to ensure that the overall process will meet the desired treatment capacity of the system. Now, with any type of biological process or chemical process, the key is treatability studies. And we have that capability from simple jar testing to show that COMAG can be an effective solution of solid separation to a full-scale BIOMAG demonstration of the technology in your biological process. And we have the ability to pilot and come in and demonstrate the capability so you can see firsthand the ability of either COMAG or BIOMAG to meet your desired treatment challenges, and you can see the ease of operation. So we have that capability and readily do this quite often to demonstrate the technology itself. Now, in conclusion here, just to close out, BIOMAG is balancing any activated sludge process, either to give you more treatment capacity using existing structure, or give you so that you can achieve a high level of effluent quality, some free up tankage so you can nitrify or denitrify. And COMAG is simply a high solids removal process, a high rate in a small clarifier or more capacity of existing clarifiers, and achieve a high level of effluent quality, and quite often can achieve close to ultrafiltration all off a conventional clarifier. And its ideal process is either to treat processed water or produce water or surface waters. We use it in a variety of applications. Now I see my time is almost running out here, so I'm going to turn it back over to Sam to, as I see there's several questions that have come in, to facilitate the Q&A period. So Sam, I'll turn it back over to you.
Thank you. So yeah, it's time for the Q&A session. We've already got plenty of questions in, but I'll just give you a quick reminder of how to submit those. So you should see the white box at the top left-hand corner of the questions box. Just type it in there and then click submit, and that gets sent in to us. We've got about 10 minutes now, and yeah, lots of questions, so I'll start us off. And the first one I'm going to go for is, can we use the COMAG in refinery wastewater treatment?
Yes, absolutely. For solids removal, we have installations of COMAG in both refinery and oil field applications across the world where we've used it and taken out particulate as well as very efficient removal of oil using a very coarse kind of DAF on the front end to remove free oil. We've taken oil as high as 500 milligrams per liter down to non-detect, as well as potential removal. You can do whatever you need to upfront chemistry-wise. If you can get it into a particulate form, we can get it to readily settle.
Thank you. Next one on the same subject is, can COMAG be used in a lime softening application?
I'll take this one, Bob. Yes, we can use this in a lime softening application. As one of the case studies we looked at, which was at the microelectronics, they were actually precipitating out calcium fluoride using lime, very similar to lime softening. The COMAG system is capable of handling high solids loadings to the clarifier in excess of 3,000 parts per million TSS feed to the clarifiers. So it can be a good application for line softening.
Thank you. Next one I've got is how does this technology compare versus DAF?
DAF is dissolved air flotation. Well, with dissolved air flotation, you're trying to float stuff. With COMAG and BALLASTED technology, you're trying to settle stuff. So they're sort of opposite in technology from that standpoint. But sometimes, as Bob just mentioned, we may need DAF or water separator as a pretreatment, depending upon the amount of solids and how much is floatable and how much can sink. I mean, if it's a lot that wants to float, then maybe COMAG may not be the right technology to use, because you may have to just add too much magnetite to the system. But generally, you may add a coagulant, which may absorb some of the floating material, add the ballast media, and then everything will sink just fine.
Yeah, and I'll comment on that from a standpoint of an OPEX for DAF versus COMAG. Outside the technical differences, very similar from an OPEX standpoint, or even maybe cheaper with COMAG. I mean, it's conventional mixers and not a lot of horsepower. The makeup magnetite is very inexpensive, so it's conventional gravity flow through the COMAG system. So there's not a lot of OPEX costs associated with COMAG.
Okay, thank you very much. Next question I've got is, what is the experiential range of loss of the magnetite through the process that cannot be recovered?
Well, let me explain twofold here. If you look at a COMAG system, we're typically getting about 99.9% recovery, and the best way to describe what's lost in the sludge and we don't recover is for about every 1,000,000 gallons of water treated, you lose between 5 and 7 pounds of magnetite in the sludge with the COMAG process. Sometimes it's a little less than that, but to be conservative, somewhere between 5 to 7 pounds. In the BIOMAG process, it all depends upon how many pounds or kilograms of BOD you're removing for the system and your wasting rate. And I guess the best way to explain it rather quickly is coming off the bottom of your clarifier, it's typically going to be a TSS somewhere between 2 to 4%. Now, half of that's biomass, half of that is magnetite. Now, that will go through the recovery process, and I'll recover roughly 2%. So let's say it's 4% coming off the bottom. I'll recover 2%, which is magnetite, and put that back in the process. What will be left is about 20,000 milligrams per liter of mixed liquor solids. In that 20,000 milligrams per liter of mixed liquor WAS solids will be somewhere between 800 to about 1,000 milligrams per liter of magnetite that I did not recover. And it's not really worth recovering. It's a very small percentage of magnetite. Not enough magnetite in there to inhibit or cause settling in anaerobic digestion. It really doesn't enhance the settling of that WAS stream at all. And it doesn't negatively impact it. It's just natural inerts that get carried into your WAS process.
Okay, thank you very much. Next one I'm going to go to is, why do you add MAG to RAS instead of directly into the clarifier?
It's actually a point of economics. Because you're dealing with a large amount of biosolids, it makes more economic sense, instead of having a very large recovery system to recover the magnetite through your RAS process. It's more economical just to let your biological process operate as you normally would, and then recover the magnetite when you go to waste solids, because your waste stream is going to be an order of magnitude smaller than your RAS stream. As an example, 1 million gallon per day wastewater treatment plant, your WAS stream will be about 10 gallons a minute, very small stream. So I either got to handle close to 1,000 gallons a minute recovery system or a 10 gallon per minute recovery system. It's more economical to just put in a simple 10 gallon per minute recovery system.
Thank you. Next one is BIOMAG useful only for municipal WW or also for refinery WW?
It would be utilized in any activated sludge process, so any biological process, whether it's industrial or municipal applications. Magnetite will readily get embedded into any type of biological flock, whether it's industrial type biological flock, municipal style, or even aerobic or high purity oxygen bioflock. We've been very successful in getting impregnated into it. So its application is broad, and its market capabilities is both industrial as well as municipal.
Thank you. Next question I've got is, can this be used on primary clarification, so smaller aeration tanks can be used?
Yes, we have a lot of activity doing what's called chemically enhanced pretreatment, either doing it for wet weather capacity or to reduce the BOD load on aeration basins. Chemically enhanced, and instead of getting the typical 50% BOD, 30% or 50% TSS, 30% BOD removal, enhancing that and getting up to 90+% TSS removal, and removing essentially all the particulate or colloidal BOD, which, for example, in a municipal application would be as high as 60% of your BOD can be colloidal or particulate, and we can remove that high of a BOD. Now, because you have primaries, you can do part of your primaries with COMAG and part not with COMAG, so that you can control your carbon feed to your biological process.
Thank you. Next up, does the COMAG process increase the torque loading on a clarifier rake? If so, how much?
Typically, no. It all depends on how you run the process. Normally, what we will do, if it's a greenfield or new clarifier, we will typically use torque ratings for either primary or gravity thickening type torque rates. But we've used COMAG and use existing clarifiers. Because you're still mostly moving water around, and we normally don't in COMAG run a blanket, you can use existing clarifier torque rates or torque ratings with COMAG and BIOMAG. But to be conservative, if it was a greenfield, we would typically use either a primary torque rating or a gravity thickener style type torque rating on a new clarifier. So it gives you more flexibility, because ultimately there are times where they may not be wasting and holding solids and building a blanket or process upsets, so you want to build that level of conservatism into it. And the cost of using a gravity thickening torque rating versus conventional is not a huge cost differential.
Okay, thank you. We're just going to go for one more before I wrap us up, and that is, are there any major parts that will require replacement?
With COMAG, most of the components are conventional and readily available, very low horsepower. There's not a substantial amount of wetted parts, so there's no real major O&M or replacement parts. For example, on the drum, the only real wear part on there is what's called a rubber doctor blade, which scrapes the magnetite off on the opposite side where there isn't a magnetic field. And that's a simple piece of EDPM rubber that's readily available. And every couple of years you have to replace that. Standard maintenance on pumps, we use typical centrifugal style pumps for most of our applications, so it's standard wear as far as replacement parts as you normally would. So there's no substantial wear components to the overall system, whether it's COMAG or BIOMAG.
Okay, great. So that brings us to the end of the Q&A session. Thank you for sending in all your questions. And it brings us to the end of the webinar as well. So it just leaves me to thank Robert and Kevin for what was a great presentation, and Evoqua Water Technologies for sponsoring this session.